Mathematical induction. Inductive reasoning. You first did inductive reasoning when you were into science. When scientists are investigating plants and animals, and then from their investigations, they will come up with generalizations. That is an example of induction. That is an example of inductive reasoning. So inductive reasoning is about drawing conclusions or generalizations based on investigations or observations of specific instances of events or objects one is investigating. Something like inductive reasoning is behind how Galileo discovered the initial versions of gravity, his version of gravity. So the story is Galileo released objects of different masses at a certain height, and he discovered that they fell to the ground at about the same time, which is suggesting that the rate with which they were falling is the same even though they had different masses. And he saw this not only with these two projectiles, but he saw this to be true also with many objects that has mass. When you release them from a certain height, when they are in the state of free fall, the rate with which they will reach the ground is about the same. And so he came up with a generalization, which is now what we call the law of acceleration due to gravity. So that is an example of inductive reasoning. So the reason why I am describing that to you is because our topic is mathematical induction. So the word induction there in mathematical induction is comparable to the inductive reasoning that we do in science. When objects or events repeat a pattern many times, then there must be a law that describes this pattern. For example, so you can look at this as the law, the summation of n consecutive positive integers is equal to n times n plus 1 over 2. We already proved this. Before we proved the finite sum of a geometric sequence. So you can look at this as a law. But this law came from these observations. When you add 3 consecutive positive integers 3, the sum is 3 times 4 divided by 2. That's n times n plus 1 over 2. When you add consecutive 5 positive integers, the sum is 15. But 15 is equal to 5 times 6 divided by 2. That is the part on n times n plus 1 divided by 2. By observing this, we can produce the generalization, and that type of reasoning is called mathematical induction. Another example. This is the summation of n consecutive positive odd integers. And the law is saying it is equal to n squared. So this is a generalization which came from observing this. You get the sum of 3 consecutive odd integers. 1 plus 3 plus 5, it's 9. And take a look at it. It's equal to 3 squared. Again, the law is also embedded here. That is your n squared. This is the sum of the first 3 consecutive odd integers. 3, it's equal to 3 squared. It's also true when n is equal to 5. The sum of the first 5 consecutive odd integers, 5, 1 plus 3 plus 5 plus 7 plus 9 is equal to 5 squared. That's the part on n squared. And so when you see something like that, which is true for many choices of n, then that is telling you something. That must be the law, okay? If we are comparing this with physics, that must be a law. But this one are laws that apply to integers. Theorem 2.5, Principle of Mathematical Induction. So I will now lay down the principle that is behind mathematical induction. Let P of n be a statement or a sentence about the positive integer n, And suppose that the statement is true when the integer is equal to 1. Suppose also that the statement is true for any positive integer k. Suppose the statement about k implies the statement about the next integer is also true. That's the meaning of this. If these two conditions are true, then the statement is true for any positive integer n. So this is how you reason out using mathematical induction. The first part of your mathematical induction, to show that the statement is true when n is 1, you call that the base case. The second part, when you assume that the statement is true for some positive integer k, you call that the inductive hypothesis. And then when these two conditions are true, then you are now prepared to make the conclusion. We will not yet prove propositions through mathematical induction. No, we will not do that in this video. I will just show to you the structure of the proof when you are proving through mathematical induction. First, you write the proposition, or you write the theorem that you must prove. Then, you will begin the proof. You begin by writing the word proof, and then you will show that this statement is true when n is 1. For most students and for me, I don't stop at 1. I also show that this statement is true when n is 2. Sometimes I go as far as showing that the statement is true when n is 3. Now, why am I doing this? Because I want to be convinced myself that the proposition is true. And by doing this, I am seeing the structure of the theorem. By showing that the statement is true not only for 1, but for 2 and for 3, I am now seeing the structure of the proof. Now, this is the second part of your proof. Step 2, the inductive hypothesis. So you will assume that the proposition is true for any positive integer k. Okay, look at that. Okay, if you were to look at this is somewhat similar to your proposition. You just change the dummy variable. If this being true will also imply that the statement is true for the next integer, then the proposition is true. Then the original proposition here, the proposition that you wrote at the beginning of your proof, is true. You will reason out this is true because of mathematical induction. I wish to use the domino effect as an analogy to explain to you the principle of mathematical induction. It's something like this. At the inductive hypothesis, you made the assumption that suppose the statement is true for any integer k. If this shows that the statement is also true for the next integer, the integer after k, then since the statement is true for k plus 1, it also implies that the statement is true for the next integer after k plus 1, and that would be k plus 2. But if k plus 2 is true, this domino will crash into the next domino. And so, you will have a sequence of falling dominoes, suggesting and implying that if the statement is true for k, the statement is also true for the next integer. So look at what's going to happen. It will create a domino effect. The statement is going to be true for the entire set of positive integers. That is the idea behind mathematical induction.